Hello, everyone, and welcome to our presentation on conveyor drive design. Thank you for inviting me to the Polish American Engineers Association September 2023 meeting. It's my pleasure to explain to you some of the nomenclature on how to design a conveyor belt drive correctly, and to also introduce you to the software which our company has developed to facilitate that task. So our lecture is on the topic of conveyor drive design. And in our terminology, this is referring to bulk materials handling conveyor drive design. In the next half hour or so, I will introduce you to our design software. I'll introduce you to CEMA conveyor nomenclature, and CEMA stands for Conveyor Equipment Manufacturers Association nomenclature. I will introduce you to the techniques on how to design and optimize conveyor drives, and then we'll conclude the presentation by looking at special loading conditions, most especially hopper feeder drive considerations. What you see here is a typical mobile crushing and screening plant driven by, in this case, happens to be Rulmeca motorized pulleys, both driving the screen feed, the cross belts, and the recirculating belt. That machine also is transferring material onto stackers, which are accumulating the two different cuts of material into two different piles. So let's dig into today's topic. By the way, before I do that, our company manufactures motorized pulleys, and what you see on the left is a conveyor belt drive, which has an AC squirrel cage induction motor inside the pulley shell, which is directly coupled to a mechanical gearbox. This is what turns the conveyor belt. In our company, we have to make sure that these are applied correctly so as to give a long life to those folks who use them. This is a screenshot of the interface page on the workbook, which we've developed, an Excel workbook, to go through the various steps that are necessary to calculate required belt pull and required belt power. So using our design imperial, and by the way, we use imperial units, it enables us to calculate required belt pull, TE, effective tension, using the CEMA nomenclature. It will enable us to select the pulley model, check special loading conditions, check the pulley diameter, check the radial load, check the belt strength. It'll easily and quickly plot trajectories and material cross sections through the belt width, as I'll demonstrate. It'll show us how to optimize belt speed and belt width decisions, and how to evaluate a dual drive option. And finally, which we'll spend time on, it'll help us evaluate hopper pressure relief. So let's define some nomenclature. In CEMA terminology, we refer to the conveyor length as the distance between the tail pulley and the head pulley. Tonnage rate, usually defined in tons per hour, is the amount of material which needs to be handled. Belt speed is obvious. This is expressed in feet per minute. Material lift height is the change in elevation between the head pulley and the tail pulley. In this example, it's 0 since it's a horizontal conveyor. We need to also specify minimum and maximum ambient temperature so as to derate the drive if necessary. We define the initial material velocity, the number of belt cleaners, the number of belt scrapers, skirt board length, which goes from the loading end to the discharge end of the skirt. You can see that pictured here. And we also need to define the material depth within the skirt zone. So if you look at a cross section through this point, you can see the belt trough, and yellow depicts the amount of material which would be in there at any point in time. We need to specify this depth so as to be able to make a determination on the amount of friction to be developed between the material and the skirt board itself. Here's another example of a mobile crushing and screening plant. You can see it, in the foreground, the recirculating conveyor, and here's a nice view of the takeaway conveyor. This is taking one cut from the cross belt and depositing the material into a pile. The conveyor has a certain number of rollers which have a certain distance between each other, a certain belt width, type of a drive. In this example, it's an exposed drive system. Here's the discharge pulley. and it's a certain number of feet above the tail pulley. Additional parameters which we need to input and calculate are the number of non-driven pulleys. In this example, we have 3 non-driven pulleys in the gravity take-up plus 1 tail pulley. So they would be an example of 4 non-driven pulleys. We need to key into the program the elevation above sea level, the material frictional coefficient, the bulk density, size consist, which refers to the percentage of lumps and fines, size of the lump, wrap angle, which I'll define in a minute, type of lagging, which I'll also define, type of take-up, which could be gravity like this, or a more simple arrangement typical on small conveyors, which is just a screw take-up at the tail. Type of belt, drive location, in this example, our drive is at the head, material flow, condition of the idlers and the pulleys, and the type of dual drive, if any. Additional inputs are shown here. This is a cross-section through the troughed area of the conveyor belt. You can see that we have rollers, each with a certain diameter. We need to specify not only their diameter and the distance between them, but the types of bearings that are used in these rollers so that we can determine friction. And another thing that needs to be specified is the material surcharge, so as to be able to properly calculate the cross-section within the zone. And the troughing angle itself, 35 degrees is a very typical troughed angle. Belt width, type of carcass, and the standard edge distance you can see shown there. Here are 2 examples of angle of wrap. In the example on the left, we have 180 degrees of wrap as the belt travels around the drive pulley. The example on the right shows a nested dual arrangement in which the return strand of the conveyor coming this way wraps around the lower drum, then around the top drum, and then back to the tail pulley. Lower motorized pulley is moving in a clockwise direction, and the one up above is moving in a counterclockwise direction. On the left, material being transferred off this conveyor. It's quite a fast belt. We can tell by how flat the trajectory is. Now let's have a closer look on what the discharge from a bucket wheel reclaimer looks like. Here we are. This machine is moving iron ore at one of the shipping terminals in Minnesota. The dual drive nest is down here. This is also a fairly fast conveyor. You can see because the trajectory is quite flat. Moving on, I'm defining types of lagging. Just like tires on your car, a conveyor drive pulley needs to have good traction between itself and the item it's moving, namely the conveyor belt. The most often used type of lagging is a full lagging in a diamond pattern with 65 durometer rubber. Another type of drive is shown here. This is what we call partially lagged. The reason for partial lagging is to be able to better dissipate heat from the motor, which is internal, and into the conveyor belt. We use the conveyor belt as an infinite heat sink, pulling heat away from the face of the pulley so as to keep the motor cool in a steady state. The center third is steel. Thermal conductivity of steel is superior to that of rubber, and that's why we do this. The higher the power and the slower the speed, the more likely we'll go to a partial lagging. On the right, you can see ceramic embedded lagging, which is another type of lagging, giving longer wear life and better grip. Now let's have a look at the 5 types of special loading which the program will accommodate. Hopper, which we'll talk about momentarily. Diverters, you can see the picture here. A tripper, which is 2 pulleys which are configured in such a way that they travel backwards and forwards on a long conveyor. Slider beds, which consist of some sort of slippery material such as UHMW, which is sometimes put between carrying rollers beneath the loading zone particularly. And last but not least, a belt with sidewalls and cleats. This is the equation developed in the 1950s by CEMA. This equation enables us to calculate the amount of belt pull required to overcome friction and gravity and momentum in the bulk handling conveyor belt. Once we have calculated the amount of belt pull that is required, I mentioned it previously, effective tension, or TE, always specified in pounds. Once we know that, we can convert that into the amount of horsepower required simply by multiplying the amount of belt pull required in pounds times the belt speed in feet per minute. The product of these two numbers comes out to a certain number of foot-pounds per minute. And in imperial units, we know that 1 horsepower equals 33,000 foot-pounds per minute. So we can easily convert belt pull into horsepower using the equation here. Belt pull times belt speed divided by 33,000 gives us an answer in horsepower. So how do we actually design a bulk conveyor drive? Given all of the parameters and the ambient site conditions, we select the belt width and speed. We calculate TE, we calculate the required horsepower, and we select a drive, whatever that may be. And then we reiterate, if necessary, to optimize. And when I say reiterate, I'm talking about optimizing the belt width and belt speed combination. You wouldn't want a belt too wide, or you would be wasting money by buying a very wide belt that's unnecessary. Likewise, you wouldn't want to have it so narrow that the belt speed has to be very, very fast and produce a very inconvenient trajectory. So therefore, we optimize using the program. This particular conveyor is a 15 horsepower conveyor moving bottom ash at a U.S. power plant. And this is the result of the program. I'm going to demo the program in a minute, but this is what the program generates. On the right, you'll see not only the calculated power to drive a particular conveyor belt, 32.3 in this example, but all of the various amounts of derating that is necessary, if any. We always will need to derate for drive pulley bearing friction and gear loss, but we may or may not need to derate for high elevation or high temperature. It depends on the ambient conditions. A direct drive usually is going to be in the range of 93 to 97% efficient in terms of mechanical efficiency. If we have two transmissions, such as would be seen with a gearbox and a V-belt, or a gearbox working in conjunction with chains and sprockets, we could plan on 87% efficiency, and that's important, and I'm going to explain why later. All right, the next part of the presentation will be a demonstration of the software. And I'm going to show for you how the program would calculate the required belt pull and power for standard loading conditions. So I've loaded the parameters in to save time. And in this example, we will be determining the amount of power required to move product at 800 tons per hour on a 150-foot long conveyor at 300 feet per minute. You can see that the material lift height is 9.3. You might wonder, how does he know that? The program provides a feature to do trigonometry automatically. In this example, we know the last 30 feet of the conveyor belt is inclined at an 18-degree angle. So the program automatically tells us we have a 9.3 foot elevation change. If it was a different angle, of course, the elevation change would be less. Back to our specification page, we put in the coldest temperature that the belt will see, the hottest temperature that the belt will see, the number of belt cleaners. As I said before, the length of the skirt zone, the depth of material within the zone, the number of non-driven pulleys. I realize I'm going fast, and we can always come back to this during the question and answer period. Going through the rest of the parameters, you can see where we spec the elevation above sea level. The default setting is 3,300 feet, which is essentially no derate required. Here we have limestone loaded in as a product to be handled with a frictional coefficient of 0.128. Also, limestone has a bulk density, as you can see, of 90 pounds per cubic foot. And just for demonstration purposes, I've selected a size consist, which shows 10% fines and 90% max lump size. And I'm specifying a lump size of 2 inches. Material surcharge angle, I've programmed in at 25 degrees. We've selected a 36-inch wide conveyor belt, which has a fabric carcass. The diameter of the rollers are 5 inches in diameter. The type of bearing is specified by selecting a CEMA C. The distance between idlers is 4 feet. The wrap angle is 180 degrees. The pulley is fully lagged. The type of belt take-up is an automatic take-up, such as was depicted in slide 3, a gravity-type take-up. The type of the belt is a 2-ply. This is a fabric carcass and plenty strong enough to do what we need done. The location of the drive will be at the head of the material flow, will be elevating or horizontal. In this case, it's mostly horizontal, but it's elevating at the end. We assume that the idlers and pulleys will be well maintained, and the type of dual drive is none. We're not demonstrating a dual drive at the moment, but you can see that the program works through the equation I explained previously, determines that the amount of pull required to do the job is 1,976 pounds. Since we've specified a 300 foot per minute belt speed, 300 feet per minute times 1,976 pounds, after some derating, tells us we need to install a 20 horsepower drive system. Let me demonstrate a couple other features in the program. I said previously that the end of this conveyor is inclined at an 18-degree angle. This is a trajectory plotter, and the red line shows the center of mass of the material that would be flowing if we're moving the conveyor at 300 feet per minute. The program allows us to put in an alternate speed. If we want to try different speeds, we'll just put in an alternate speed of 400 feet per minute. And you can see that this is showing that to speed up this conveyor would cause a problem if the chute, this black line represents the chute, is 24 inches from the center line of rotation of the pulley. We know from experience that if the center of mass of the material impacts a vertical wall above the horizontal center line, this chute will be prone to plugging and not flow very well. On the other hand, our design belt speed, we selected 300 feet per minute, magically falls below the horizontal center line, and the material should flow freely through. This part of the program allows us to see how full the material will be on a 36-inch wide belt at 300 feet per minute. Notice that the black line depicts the CEMA recommendation for a maximum fill, and the red line is what we have selected here. If we thought we might handle more tonnage, let's put in 950 tons per hour, keeping everything else the same. You can see that we are asking for trouble because we're filling our trough higher than CEMA would recommend, and this conveyor would be prone to spillage. For anyone who would need all of the intimate details on this solution, all of the parameters that were required to come up with this information are depicted here. And once again, this nomenclature is known as the CEMA historical nomenclature. Once we've figured out the amount of belt pull required, and we've come up with the amount of horsepower that's required, we would select the motor and transmission to match the speed and so forth and provide enough power. We would want to optimize the effective tension and the required power by trying different belt widths and different speeds if applicable. In other words, if what you try first doesn't work, you can optimize in a matter of a few minutes by using the program. We want to check the cross section as I showed before. We want to check the trajectory as I showed before, and then select the drive. For example, you could select a Rulmeca motorized pulley or anything else. You'd also want to check radial load. The program tells you how much radial load will be pressing on the shafts of the conveyor. And this is an example of a failure. just to show that it can happen. In this case, a pulley was put into service, which was 2 weeks, and it failed in less than 3 weeks. This is on the tip of a bucket wheel machine, and the amount of tension in the belt was way beyond what the end caps and bearings and shafts of the pulley could stand. Once you've done what I said, you want to check the slack side tension. That's the tension on the bottom of the conveyor to make sure you have enough slack side tension to resist slippage between the pulley and the belt and resist sag between the rollers of the conveyor, the support rollers. And of course, we check total tension, belt strength, and pulley diameter. Here's an example, small video. You can see that this pulley system definitely has not been designed correctly, and the pulley is rotating much faster than the belt is. So this is a slip problem, which could be corrected by tensioning the bottom strand. These numbers will allow us to compare different kinds of drive systems. The one on the top is a direct drive system using a normal 3-phase motor and one gearbox, such as you would see in a motorized pulley or a right angle gear reducer, a direct drive. They're typically in the range of 93 to 97% mechanically efficient. We'll compare that against a 3-phase motor with 2 transmissions, a gearbox and a V-belt setup, or a gearbox along with some chains and sprockets. It's well documented that mechanical efficiency is below 90%, we'll say 87%. Last but not least, although this is an exaggeration, here's an example of a 3-phase electric motor working in conjunction with a worm gear reducer to produce the same speeds as I was talking before, same belt speeds, but it's notoriously inefficient. How do we compare this? Well, we know that 1 horsepower equals 0.746 kilowatts. And once we know the power, we can convert after a derate for mechanical efficiency. We can convert horsepower to kilowatts, as I just said. And the direct drive system would be 15.75 kilowatts. The case of the 2 transmission set would be 17.25 kilowatts. And to do the same amount of work with a worm gear reducer would be 21.45 kilowatts. Now, if that system were working 24 hours a day, 7 days a week for 50 weeks per year, or 8,400 operating hours per year, the direct drive would consume 2.65 million kilowatt hours per year, whereas the 2 transmission set would consume more, 2.9, and the worm gear reducer would consume 3.6. And when we compare the 2 transmission set with the direct drive, we would save $25,000 a year by using the direct drive method if the utility is charging 10 cents per kilowatt hour. Comparing a direct drive with the worm gear reducer, we save almost $100,000 because the direct drive is so much more mechanically efficient. So in the remaining part of this presentation, let me explain one special loading condition, namely the hopper feeder. On the left, you can see 2 hopper feeders beneath a big bin at a quarry in Georgia moving limestone. The one on the right is a single paint laid hopper, which could be loading material onto a conveyor belt, which could be pea gravel, or it could be corn, it could be anything. So here we have an example of a typical hopper, a single paint load hopper. It has a certain opening width and a certain opening length. The conveyor here is beneath the bin. This is empty, this is full. What is the force required to overcome this drag? This is like a snow plow, plowing snow on the street. If you could consider the conveyor belt moving this way, that makes this edge of the hopper almost like a snow plow pushing snow that way. How do we calculate it? We could care less how much material is in the hopper. The only thing we really care about is the size and shape of the active volume of material, because that is all that will be felt by the conveyor belt. This is called hopper arching theory. It's well documented that a parabola can approximate the amount of active material which is pushing down on the conveyor belt. So what is the force required to overcome this drag at this edge as the belt pulls material from beneath this particular active zone material. We have simplified this methodology by saying you can approximate this parabolic shape conservatively by using the shape of a prism. And a prism is defined by a hopper opening length, so much width, defined by the geometry of the hopper, and the height. And the height is set 3 times the width or 3 times the length, whichever is smaller. That will conservatively approximate a prism, which will more than equate to what a parabolic shape would weigh. Once we know the volume in cubic feet, we simply calculate the weight by using the bulk density. So many pounds per cubic foot times so many cubic feet gives you so many pounds. To convert that weight into a horizontal force, which we call drag load, we simply multiply by 0.5. So 0.5 times the active weight would be the amount of extra drag required to overcome that load. Now, you're all engineers, so I'm showing an excellent idea in reducing required drag, which is hopper pressure relief. If we have the same dimensions in the hopper length, opening length and width as before, but we decide to weld in angle irons, this cross-section view AA is a cut here looking at the bottom of the hopper after angle irons had been welded in. If we change the opening from 1 opening to 4 openings, we do something amazing, because once again, the equation is the same as before. Height is set to equal 3 times the width or length, whichever is smaller. And as you'll see in a minute, the amount of volume decreases by putting in hopper pressure relief. And allow me to run this animation for you. First, we see a parabolic shape that would coincide with 1 hopper opening. And in this example, it's almost 154 cubic feet. Now, if we were to install pressure relief, we would no longer have an active volume of 154 cubic feet, but rather a total of just under 77 cubic feet. You'll notice that the amount of volume is 1/2 that amount of volume. If your product is small enough to flow freely through those 4 openings, we strongly recommend that designers use that option. Now, this will be my second and final demonstration of the program. I've preloaded the hopper parameters. We don't have the same parameters as before. This is a short conveyor, very typical of a hopper feeder, 10 feet long. A typical tonnage rate would be 250 tons per hour, quite low. And a belt speed, which is also relatively low, 100 feet per minute. I've loaded in all the other parameters. And what I've done is I've made the hopper opening 0. And you'll notice that if we have no hopper to move this amount of product at that speed on a conveyor that's that long, we only require a little over 1 horsepower. But let's say we actually have a hopper, which has an opening width of 36 inches and a length of 66 inches with 1 opening. Notice that our 1.1 horsepower becomes 23 horsepower because the amount of drag exerted by that active load is almost 7,000 pounds. And so a total of 7,027 pounds times 100 feet per minute gives you an enormous amount of power required to withdraw the product. But now watch this. Once again, we're at 23 horsepower with 1 opening. And if we convert it into 4 openings, it's no longer a 23 horsepower, but 12 horsepower will do the job. And if the material is small enough to fit easily through those holes, it's well worth doing because the amount of power that would be saved. Let's see what that means. With 1 opening, we had an active volume of 154 cubic feet. the drag load calculated out to the number you can see here. And at the 100 feet per minute belt speed, once we allow for some drivetrain losses and so forth, we know that the amount of power required for one opening is 23.2 horsepower. And with 4 openings, we cut that active zone in half. And so now the amount of power is just about in half. What does that mean? Well, that means if you're running 24 hours a day, 7 days a week, 50 weeks a year, and the utility is charging 10 cents per kilowatt hour, the amount of savings by sticking in $50 worth of angle iron is almost $7,000 a year. Well worth doing. So in a short period of time, I've shown you our software. I've presented CEMA nomenclature. Quickly, I realized, but nonetheless, I hit the high points. I showed you the concept of designing and optimizing conveyor drives in a standard loading configuration and also on one special loading condition, namely hoppers. And I thank you for your attention. And at this time, I'm certainly willing to stay as long as you would like to answer any questions